We have Alan Booker here today. He's got a presentation for us, carbon negative mass heaters. I have never seen this presentation. I believe it's hot off the press. So Alan has only recently seen this presentation. And I know that when I try to bring this topic up, I get a lot of pushback. And so hopefully this will enlighten me so I can answer these questions. I have some vague ideas of what he's going to say, but since it's Alan Booker, I believe I'm about to learn far more than I knew before, even though I'm supposedly an expert in this space. So Alan Booker, please teach me about carbon negative mass heaters.
Well, yeah, Paul, I think maybe the best way for me to position the whole discussion we're about to have is this. I put some of my credentials down at the bottom of the presentation for a reason. And it is because I do consulting in green and regenerative buildings in a lot of different venues, and sometimes for very large projects. And so I'm a LEED accredited professional in building design construction, a well accredited professional. That will come in play here because well building has a lot to do with making certain that buildings are healthy for people to be in. Living Futures Accredited also comes in here because that has to do with the International Living Futures group and their Living Building Challenge. And I've currently got some projects going on where we are looking at rocket mass heaters in Living Building Challenge buildings. And they have said, no combustion. We won't allow any combustion. And I'm fighting them on that. And I have been talking to their tech team about changing their rules by showing them that I can use combustion in a way that's actually cleaner and better than any other option. And so this presentation is me beginning the process of putting it together in terms and in a way that I can present to a group like the tech team at ILFI in order to, in their language, and to address their concerns, in order to get them to approve a carbon negative mass heater in what are the world's greenest buildings in the way they present it. There are only 30 full LBC buildings in the world right now, and I'm working on 3 more. So we're looking at getting what I've decided to call a carbon negative mass heater in that program. And they said, maybe we'll give you an exception. And I said, I don't want an exception. I want you to change your rules. So we're going there. And the GRP, by the way, is Green Roof Professional. And that's where we're using green roofs in buildings for high performance. So those are just some of my credentials that are appropriate to this particular conversation. So I'll just say for those who are coming in the door and wondering why I'm calling a carbon negative mass heater and not a rocket mass heater, it's because here's how I positioned it. I am basically putting together a white paper that defines a thing called a carbon negative mass heater system. And it is not prescriptive. It does not say that you must use a rocket mass heater. It describes a system for using biomass combustion in a carbon negative way in order to heat a building. And it just so happens that a rocket mass heater is the exemplar that we're going to use because it's the one that we have developed today. But I didn't want to write this whole thing up in such a way that if we innovated some other things in the future, that we have to go back and redefine it, right? So it's defined in a system perspective, and then it uses a rocket mass heater as the case study, okay? So with that, let me jump in and see what we can do. All right, so one of the things, having to constantly be involved in these discussions around green buildings and regenerative buildings, there's a lot of discussion in that arena towards zero combustion and full electrification as the ultimate goal. I see continuing education stuff on this all the time and presentations on this and what's called whole building electrification. This is a huge thing you're seeing in the industry right now. And so here is an example of one of the graphics that you'll see from the industry, right? From Edison International, their whole building electrification. So they're, okay, let's get rid of combustion for building heating, especially natural gas. Let's get rid of it in the kitchen where you have, stoves and ovens, and go towards induction technologies and so forth. Let's go to basically everywhere that we had any sort of combustion in the building. Let's get rid of that and go to electrification. And of course, the reason for that is that the idea is that we are trying to create more and more sustainable ways of creating electricity from natural and renewable resources. And I think as we go through this, what we're gonna see, and having done a lot of that, where I'm doing full building electrification, except for cooking and heating, what I have found, of course, is that full building electrification has some issues in that and we'll see that as we go through. I'll give you a little spoiler alert and kind of say what we're going to find is that some of the times when we need to use combustion is the moments when things like solar are at their weakest. And so if we go to full building electrification, all of a sudden we find ourselves pulling a lot of power off the grid with all the nerdiness that implies. Okay. So the purpose of this particular presentation is to show the specific type of biomass combustion system actually turns out to be a superior option in a sizable number of cases to full building electrification. So I came up with the term carbon negative mass heater because, of course, one of the huge things you hear over and over and over again is carbon and carbon accounting. I'm a member of several different groups that are looking at the carbon footprint of everything, the carbon footprint of a building, both embodied, how much does the building take to build, and also operational carbon. Yes, Paul.
Thanks for noticing my hand. I was wondering if that would work. But I wish to ask a political question, if you don't mind.
Okay.
And that is, clearly you are a man of science and climate change.
Yep.
Are you a person who says yes, no, or maybe?
Yes, the climate is changing. That much is completely clear. I'll put it to you this way. I go out and I talk to fourth and fifth generation farmers on the land, right? Who have history on the land back 4 or 5 generations. And to them, there is absolutely no question that what they're seeing today is different than the family history back on the same land for 4 or 5 generations. So the climate is shifting, and that is, to me, highly evident. And so what I would say to that is that climate change, however, is a symptom of a complex of much deeper problems. So if you come to listen to everything I have to say at, for example, the permaculture design certification course, we'll talk about climate change a little bit, because I'll talk more about how we have to change our designs to deal with it. But to me, I spend a lot more time dealing with the underlying issues and how to regenerate natural ecosystems, because if we can do that, we'll solve problems like climate change. So, but what I get into is if I'm in the discussion in the green building and regenerative spaces like LEED and WELL and Living Futures and so on and so forth, carbon is a huge thing they want to talk about. So by naming it this, I am addressing front and center a concern that they are pushing, even though I still think that it is a symptom instead of a root cause.
So I agree with your analysis. And I guess one of the big things is that I wish to embrace audiences, or at least in my audience, the people that are concerned and the people that think those people are fools. Mm-hmm. And so, and there's a lot of talk about there's other political agendas at play that wish to over promote, carbon issues for their political gain. And it's kind of like, I don't care.
Anytime that there's enough money moving, there's going to be politicalization of a subject like this. I
think that the important thing is that the theory is either true or it is not, or it's something in between. I think we can say that as a mathematical 100% truth. And in the meantime, I think that the people that are very concerned about carbon issues are pursuing red herrings to solve the problem.
There's a lot of that, yes.
Whereas I kind of feel like at the very least, this is a real solution.
And that's what we're going to try to show throughout this whole presentation. Yeah.
Excellent.
Yeah.
I'm glad we had this chat. I'm ready to shut up now.
So a carbon negative mass heater is a complete building heating system that integrates a high efficiency biomass combustion core with a thermal mass to create a heating system that provides net sequestration of carbon, removing more from the atmosphere than it releases. So as I said, this system description is generic to allow for future innovation. But we're going to use a specific configuration of a rocket mass heater as an example for this presentation as we get into the details. Okay, so first we have to talk about the carbon cycle just quickly, because we're going to call it a carbon negative mass heater. We kind of need to talk about that, right? So this particular diagram is just a quick example of the kind of carbon accounting that we do as we start trying to figure out whether, how in the world we're getting to the point where we're now over 400 parts per million carbon dioxide in the atmosphere, when pre-industrially it was down below 270, right? And so we see here in blue what we call pools, that is places that carbon is held. And then in the red, you see fluxes, that is places where carbon is moving from one pool to the other. And these numbers give you a rough feeling of about how much there is. Notice what's interesting here is plants, soils, and atmosphere, just to give us an order of magnitude, okay? So these are petagrams, by the way, but let's just look at relative numbers. 750 petagrams in the atmosphere about now. Plants are around 560, but soils are around 1,500. In other words, we have about 3 times as much carbon sequestered in the soil as we do in plants, round figure. And what you're going to find is the way that I have engineered the carbon negative mass heater takes that dynamic into account quite a bit. We're going to dynamically sequester the carbon into plants and soil. That's what we're going to do in this process to become massively carbon negative, pulling carbon out of the atmosphere and pulling it into the plants and the soil, okay? So I have a definition that I use when I'm presenting to technical audiences. This is my definition. People are starting to pick it up. And it's what I call dynamic versus static carbon sequestration, because to me, they are very different kinds of dynamics in the carbon cycle. Dynamic sequestration is when carbon becomes involved in a life process that keeps it out of the atmosphere during the period the carbon is involved in that process. Typically, some carbon atoms are leaving as others are joining, but the net total carbon sequester is either constant or expanding while the life process continues. And that's where we talk about the plants, but also the soil, because a lot of soil organic matter, which is where we generate a lot of what's called soil organic carbon, is created by life processes, specifically microorganisms in the soil, either saprophytically breaking down organic matter from the soil surface, or actually to a larger degree, building soil organic matter based upon carbon given to them by the exudates of plant roots. So that is what we call dynamic sequestration, because obviously, if you cut down the forest and burn it, it goes back into the atmosphere. If you get rid of the living cover over land, then the soil organic matter will begin to break down, will photooxidize, and you'll start to see more and more of it returning into the atmosphere, versus static sequestration, which is a chemical or mechanical process that locks up carbon in a chemically stable form or location where it will not react and return to the atmosphere, which is exactly what happened when nature created fossil fuels. It took huge amounts of carbon, put them into a stable chemical form, and then ended up sequestering them down in geological strata in which they were they were not going to basically go back into the atmosphere on their own accord, unless something massively happened geologically. So I'm going to call that static sequestration. And what you see is that early on, a lot of a lot of money was flying around thinking about how are we going to solve the atmospheric carbon problem using static sequestration methods. That is high-tech, high-energy methods of trying to build machines to pull carbon out of the atmosphere and stick it back down in the ground. And as more and more work has been done on this, we've been able to, in my estimation, it's showing itself to be more and more economically unfeasible, more and more technically difficult to do. And I think it's just basically the only reason it's being pursued right now is because there's a lot of research dollars flying around to fund the early work. I don't think we're going to find that these methods are going to be a way of really dealing with the problem at scale. Maybe I'll be proven wrong, but I'm very I'm kind of skeptical at this point in time. And when you start looking at the numbers and how much it would take to sequester the amount of the number of petagrams of carbon we're thinking about, and how many of these things and how much time it would take to run them and everything else. Yeah, maybe we can build some of this into the actual immediate release. That is, when you're actually burning fossil fuels, immediately capture and store at that moment. That's actually much more efficient than trying to pull it out of the atmosphere once it's already released. So that may have a little more possibility than trying to pull it out of the atmosphere. But if you want to pull what we already have in the atmosphere back into some sort of sequestration, then dynamic sequestration has a lot of advantages because it is a process that we can do for very low cost at very large scale. So, of course, where we are is that fossil fuel carbon release has been taking carbon that was statically sequestered in the earth and turning it into carbon dioxide. And that's why I said before, we were raising levels from what was around 270 parts per million before industrialization to over 400 parts per million today. And so when we start talking about tons of carbon dioxide, you have to realize that burning 1 ton of coal will release over 2 tons of carbon dioxide because coal is almost pure carbon. It's very high carbon. And so you get a ton of coal and you burn it, then the carbon is pulling oxygen atoms out of the atmosphere and burning them. And now the atomic weights of the carbon and the oxygen are combining to create a heavier thing called carbon dioxide, which is why burning a ton of coal actually releases over 2 tons of carbon dioxide into the atmosphere. Okay, so this is where the possibility of dynamic sequestration comes in with forest carbon sequestration. There is also mangrove sequestration, which is huge. And then there are sea forest sequestration, which can also be huge. But for what we're looking at today, the part of the carbon cycle that we're looking at as our sequestration mechanism is the carbon cycle of terrestrial trees. Yeah. So this is a diagram from the state of Minnesota showing the inputs and the outputs, how carbon is pulled out of the atmosphere and sequestered in both the biomass of the tree and, very importantly, in soil organic carbon, both from leaf litter that's saprophyllically broken down into the soil horizon and upper soil horizons, and then, of course, from the root exudates feeding fungi and bacteria as they exchange sugars with the tree, building carbon biomass in the soil. And so this is, most people, they don't think about it, but we conceptualize, when we think of a tree, we think of a tree growing up out of the ground. And that's actually not a completely accurate way of visualizing it, because 90-some% of the mass of a tree comes from carbon, oxygen, and hydrogen. And the vast, vast majority of that carbon is actually pulled out of the atmosphere via photosynthesis. And as a result, it's actually, and of course, water comes in both from the roots, but also coming in from, and oxygen coming in from certain other processes. But it's almost as accurate to think of a tree as condensing out of the atmosphere as it is to think of it as growing up out of the soil. There's that much of the mass of the tree that's coming out of the atmosphere, right? And at the same moment, you have to realize that there's a huge amount of that excess energy from photosynthesis going into exudates into the soil that's feeding the soil life to create soil organic matter. And it can actually outdo the amount of carbon that we end up sequestering in the biomass of the tree over time. So we have to look at both of those in order to think about how we're pulling carbon out of the atmosphere, right? So here's a diagram from the Forest Service, where on the right, they're showing that fossil fuel use is an open system where CO2 remains in the atmosphere, right? You pull it up out of the ground, you burn it, and then the carbon goes up into the atmosphere, at least until we figure out a way of capturing it at combustion and putting it back. But of course, when you burn it in something like a vehicle, that's open cycle for now. We don't know any way of grabbing the exhaust coming out of the back of your vehicle and taking that carbon and doing something with it, right? Maybe we could retrofit power plants and other fossil fuel burning things, maybe, we'll see. But in the closed loop biomass, what we end up with is growing forest removing carbon from the atmosphere. And then of course, that going around bioenergy from forest biomass can substitute for fossil fuel energy. Well, that gets really big and industrialized. I find that a lot of our regenerative systems work better as a smaller, lower tech distributed system, which is what we're going to be talking about here. And then when you combust it, part of that carbon dioxide is returned to the atmosphere, but only part. And that's where our possibility is. Now, one of the big complaints about biomass combustion has been that there are a lot of biomass combustion approaches where it's like, yeah, they're cutting down forest over here and turning it into something like pelletized, biomass, and then putting it on trucks and shipping a couple states away and burning it there. And as soon as you do that, you've got several problems. And that's not the system we're talking about. As a matter of fact, you're going to see we have defined the system that's not allowed. So pelletized biomass coming from a biomass a couple states away, where that your money of buying those pellets is subsidizing somebody cutting down the forest that's providing all kinds of important habitat, not allowed by this definition. Yes.
Oh, there, you answered my question. Just exact. I was going to say, does your definition permit this? And so yeah, your definition does not.
Definition does not, right? Yeah, because if that's answering one of the big concerns, and it's a valid concern that a lot of folks in the green building industry have, right? So it's defined into the scope of this system. Okay, so now let's summarize why biomass combustion can be carbon negative. Burning biomass will return only part of the carbon sequestered during the growth process to the atmosphere. Carbon is dynamically sequestered by the things I've mentioned before. Leaves and woody biomass falling to the ground, being decomposed by saprophytic organisms, root feeding the soil food web, and the remaining living biomass of the tree if it's managed via coppicing or pruning instead of dead fill. Okay. All right. Now let's get to the definition. How are we going to define a carbon negative mass heater? Okay. And so it's a system, and therefore let's define the system components. And of course, the first component of the system, here's the definition, is on-site or local regenerative biomass production. Regenerative biomass production that builds soil organic matter is the key to making the system carbon negative. Keeping production on-site or hyper-local eliminates embodied energy of transport and the problem of cutting ecologically important forests for biomass. Production options include coppice, pruning, stormfall harvest, or regenerative forest management. And that could include proper regenerative thinning cuts and other regenerative forest management techniques practiced locally, okay? Our case study, when we get there, is going to be of the coppice system. And the reason is I'm able to show exactly how carbon negative we can go using a bunch of research we found from a bunch of information on coppice, okay? But stormfall would include some of the things, Paul, you've talked about, which is you can go out and gather sticks and wood and so forth that just comes to the ground during storms. You can use pruning as you go in and prune food forests or other areas, or actually any wood that comes from very local on-site regenerative forest management.
So in order to qualify as a carbon negative mass heater,
Yes,
then part of the definition isn't just the contraption for heating your home.
yes,
It must include local source for the wood. So for
Correct.
example, if you're in a city, you can't do it. It cannot be done. Or
you start to build coppice systems into your cities. I'm starting to do some consulting work with folks that are looking at how do we do regenerative cities at scale. And so the land use patterning that I'm putting in creates agroecology and fuel wood. Our goal here is to, as you'll see, there's other components here that are equally important. And the next component that we go to is to drastically reduce the amount of wood we need so that the number of cases that we can do step one is much higher. Yes.
I want to ask something from the previous slide real quick. You've shown a lot of different systems for where our carbon might be coming from, and in order for it to be a carbon negative mass heater, then the fuel source is critically important.
Yes.
I'm getting to the point now where I think that there could be an apartment somewhere, and it could be heated where they have effectively a rocket mass heater. And I don't know, maybe we could make some modifications to a rocket mass heater, or maybe as is it'll work. But for the most part, having them save their cardboard boxes that they get, like they had something delivered in a cardboard box over the summer, and they saved all of that. And then if they were able to heat their apartment over the entire winter using nothing but the cardboard boxes and other papery goods that they naturally accumulated in their waste over that year, would that qualify in your mind as a carbon negative mass heater?
I have to do the numbers on that. I can't tell you right now. My feeling is that we're going to have to run all the carbon numbers. You're going to see we're running numbers here. We're not just waving hands. So I can't answer that question. I do, however, see a couple of things I want to answer real quick in the chat. One of them is about the polycyclic aromatic hydrocarbons present in wood smoke. Evidence that the high temperature burn reduces these toxins. Yes. Secondary burn pretty much completely reduces them. We'll get to that in detail. The other one was deserts. Yes, we can grow trees in deserts. If you want to know how, come to the PDC. We'll cover it in detail. Okay. We can regreen the deserts, and that is being done in a lot of areas right now. As a matter of fact, desert settlements have to be reforested in order for them to be sustainable and regenerative over time. So I'm going to go forward from here. Okay, high performance building envelope. So a energy efficient building greatly reduces the amount of energy required for heating and reduces fuel requirements, therefore reducing emissions and also fuel load requirements, right? Reduction of uncontrolled drafts increases building comfort. And notice I said uncontrolled drafts increases building comfort. What you're seeing here is when we do PERS ratings, which is Home Energy Rating System ratings, we use infrared cameras like this to see where the buildings are losing significant amounts of heat in the wintertime. And so one of the aspects of this system is that it's coupled into a high performance building envelope, right? And there's a couple different ways we can do that. Strategies would include a properly insulated building. As you saw, I'm a green roof professional, so I use green roofs on buildings, drastically reduces the energy footprint, and also cooling, drastically reduces cooling when done properly, passive solar gain, and thermal mass and thermal inertia. We use all of these strategies so that we move towards the rocket mass heater or the carbon negative mass heater being a auxiliary heat to all of the to some other methods, such as passive solar and annualized thermal inertia, or daily thermal inertia, according to where you are, right? Because according to where you are, your thermal inertia strategies are different. If you're in a, again, desert environment with high diurnal swing, then you might be doing diurnal thermal inertia. If you are in an area with, like Montana, you might be doing annualized thermal inertia. That's a valid way of doing it. Passive solar is available in many areas in the temperate zones, and green roofs are a huge moderating effect. And I don't have time to get into all that, but those are some strategies we can use. Okay. Third part of the system, makeup air and IAQ management system. This has to be engineered into a carbon negative mass heater system. So a combustion heat system needs a low resistance source of air for efficient operation. Many manufactured approaches, that's, wood stoves and so on and so forth, use a fresh air vent coming from outside. But certain high efficiency combustion cores function better using room air. If this is the case, a source of makeup air is needed to replace what's being used by the heater. Whatever the solution, it needs to maintain a high indoor air quality, IAQ. Remember, I'm having to build buildings that meet the well building standard, right? And so I have to think about, if I'm going to use combustion, here comes the next set of questions. What about indoor air quality? So we're going to have to address that, right? So if the building is not tight, air will be pulled in through cracks, creating drafts and reducing performance. If the building is tight, this can create negative pressure, causing a number of problems. And in the worst case, it can cause backdrafting, right? So here's a picture, for example, a makeup air system for a home showing how makeup air can be brought in to make up, for example, the exhaust fan in a kitchen, right? Okay, so this can be highly inefficient if it's done in a dumb way, right? So I have two options for doing it smarter. We're going to look at those. Yes, Paul.
I guess I wanted to talk about, can't the air going, first of all, it shows air going out. Is it going outside? That red air, is it going outside?
That's correct. Yes.
And
so in a kitchen vent, if it's properly vented, it should be going outdoors.
So it's possible that one of the things you're about to show us is like an air-to-air heat exchanger.
So one possibility, if you want the high-tech solution, is a DOAS with ERV. Yes, these are the industry terms for it, right? A dedicated outdoor air system called a DOAS. This is where we bring in, here's the thing, when you are in a system where you have an engineered heating and cooling system and you are heating with radiant heat, the radiant heat does not solve your ventilation problem, right? So if you have a bunch of people in the room, even if the mass heater is not contributing a single bit of carbon dioxide to the room, the people are. And you'll start seeing the carbon dioxide build up in the room. So even if the carbon negative mass heater is providing all the radiant heat you need, you still need ventilation if you have enough people in the room. Now, we've been doing some measurements. One of the architects I'm working with, Gary, has been measuring CO2 in his bedroom when he and his wife are sleeping. All they do, there's nothing except a radiant heater in there, and there's no demand ventilation. He just closes the door and they sleep at night, and they see CO2 going up to like 1,500 parts per million as they sleep in the evening, which actually contributes to poor sleep. So he's had to actually do things to remediate the ventilation. It's called demand ventilation, where we look at the CO2 caused by the people, and if the CO2 gets above a certain threshold, we start bringing in fresh air so the people have a low enough carbon dioxide to be healthy. We'll look at numbers in a moment, okay? When we get into some more stuff with IAQ. So an ERV, an energy recovery ventilation system, is that heat exchanger, right? A form of heat exchanger recovers heat from the exhaust air. So you see these kinds of things used where you have VRFs, variable refrigerant flow heat and cooling systems. But You can use a system like this with the carbon negative mass heater or any other radiant heat system where you need to provide the ventilation, because in a radiant heat system, ventilation is separate from heating, okay? So you could use a DOAS with an ERV. And in certain larger building situations, that's where we might have to go. If you want the low-tech version, or maybe the higher-tech version, because it actually is completely passive, you can use passive geothermal ventilation with annualized thermal inertia. And this is a conceptual diagram of something I'm using here in the Southeast right now. We are basically taking and putting about 120-foot run on this pipe, okay? You can see there's an intake well out at one end, and then what's called the ATI's annualized thermal inertia zone around the pipe. It then bends up at a 45-degree elbow, because a 90-degree elbow, 90-degree elbow would present a huge amount of resistance to passive airflow, right? And the whole thing drains away from the building at a minimum of a quarter inch per foot of run. And what you end up with here is you design the building for passive chimney effect. As the rocket mass heater is heating, the hot air rises and a little bit of it escapes out the top as a chimney, and it pulls fresh air in. So we're using the energy that coming from the rocket mass heater to drive the ventilation as well, okay? Now, the fun thing that's happening is that this is engineered in such a way to create a 6-month lag. So when you do ventilation in the wintertime, the ATI zone around the pipe has been pre-warmed over the summer. And then over the winter, you're pulling heat out of it and chilling it. So by the time you get into the summer, now when you pull fresh air in for ventilation, you are pre-cooling the air. And when you do so, you dehumidify it to some degree, and then that water drips out. That's why the whole thing is tilted away. So this is a
about mold growing in the pipes.
Yes, there is, and that's why it also is designed for a clean out. If you have a 90-degree, then it's much harder for a clean out. This is smooth walled pipe so that it drips back and will dry out as quickly as possible. And also being smooth walled, we can do it. Yes, you can have radon infiltration. You have to engineer for that if you have it. What you'd end up doing is the pipe itself is typically a pipe that will not allow radon infiltration there. What you have to do is make certain that the intake of the pipe is not pulling in radon, right? And that the vapor barrier at the bottom of the building has proper detailing around the pipe entrance to make certain that radon isn't coming in there. Yes.
Radon is 7 times heavier than air. So it just seems like on where your diagram is, you have a little bit of a dip below your air intake.
Yes.
It just seems like on the one hand, you're tempted to have a little bit more of a dip to collect the radon,
Yep.
but it seems like eventually it will pool up and be taken in by your pipe. So it kind of does seem like if you are in an area that has radon issues, you might need to have a way to pull some air out of the bottom of that well. And by air, I mean radon, and disperse it away. So that way this is not taking in that radon.
Actually, the passive way to do that is to put a V redirector underneath the pipe. This is a vertical pipe coming down, right? And
Right.
we want the liquid to be able to go down into the ground. So underneath it, radon has a tendency to bubble up. So we can actually put a deflector to deflect the radon away. There's some details we can get at time to get into that in full detail. But if we're in a high radon area, we would have to engineer for that.
Okay.
Yeah. Okay. So yes, you can engineer for that. Okay. But again, since this is designed where we can run cleaning through the pipes quite frequently for this. It's just part of the maintenance of a system like this. And we'll just kind of go on from there. So let's talk about IAQ measures real quick. Okay. So I always design to meet tier 2 of the enhanced air quality requirements of the well building standard. For people who are familiar with the well building standard, this is the well building standard version 2. And so what that means is that I'm wanting to make certain that PM 2.5 is 10 micrograms per cubic meter or lower, and that PM10 is 20 micrograms per cubic meter or lower. Okay. Now, what in the world is PM 2.5 and PM 10? For those who aren't familiar with all this verbiage, PM, of course, stands for particulate matter. 2.5 stands for 2.5 microns or smaller. 10 stands for 10 microns and smaller. Okay. And they tend to come from different places. A lot of your fine combustion particles can come as PM 2.5, but there's other things that can come in under PM 2.5, including pollen and so forth. Some of your larger dust particles come in as PM10 and so on. So we're trying to manage to make certain that we have in the building, right, these very low particulate matter, which means we can have no backdrafting. We have backdrafting, we're going to get particulate matter into the air of the building. That means that makeup air has to be done properly so that we never backdraft, right? And that the system has to be designed to run properly so that there is no backdrafting. Therefore, if it backdrafts, it does not meet the requirements of a carbon negative mass heater, okay? We should be able to go in with our air quality monitor, and you can see there's air quality sensor as an example of it from SenseWare. It's one of the companies I've worked with a little bit. We can measure in real time a bunch of air quality standards, including particulate matter, okay? PM goes too high because of the heater. It's not designed right. It fails the standards for meeting the definition of a carbon negative mass heater. Okay. Another thing is organic gases, also known as volatile organic compounds. I see Bo has a question, so let me see if we have anything we need to address real quick.
Yeah, Jim asks what should be the separation if using more than one pipe in such a system. Yeah,
I typically am trying to get one every about 250 to 300 square feet of building. And so I try to keep them maybe at least 10 to 12 feet apart, because you don't want them to run into each other's ATIs, right? And the ATI zone is typically can be 4 or 5 feet around. So, I try to keep them far enough apart that they each have their own ATIs. Okay. Anything else, Bo?
No, that's great. Thanks.
Okay. Part 2 of the enhanced is the volatile organic compounds, which means that we're not going to have any of these. Well, if you build a carbon negative mass heater out of the materials recommended, then it will not off-gas any of these, either into the building or as external exhaust. So don't have to worry about that. How about carbon monoxide and nitrogen dioxide? If you have a properly running carbon mass heater, during combustion, you will meet this in exhaust outside the building, right? Which is really funny because we're talking, this is indoor air quality, right? And if we're drafting properly, no carbon monoxide, if any is being made during the beginning of the burn or the end of the burn, it's all, what little bit is being made should be going up and out the chimney. It should never be coming back into the building. Same thing with nitrogen dioxide. If we have a properly running, for example, rocket mass heater, in most cases during the clean part of the burn, which is the vast majority of the burn, these two would be met at the exhaust coming up the chimney, okay? So we're meeting all of that, right? And of course, the last one we want to look at is indoor carbon dioxide levels. Now, the well building standard requires demand controlled ventilation, DCV, to maintain regularly occupied spaces below 750 parts per million of carbon dioxide. I personally prefer 650 parts per million as the upper limit, because you start to actually, sensitive individuals start to feel it above 650. So what I'm looking for is a demand ventilation system that keeps it at that. It's bringing in enough fresh air to keep the indoor ambient below 650. 750 would be my high end. You'll see some places that set their demand ventilation like 850 or even 1,000. I don't like that at all. And because I think that up to 1,500 is moderate. There have been research, I won't cite it all here, that people start to get into very measurable decreased cognitive function at 800 to 850, okay? So I try to keep it around 650, definitely below 750, okay? So now we get to part 4, right? So we had our fuel source, we had our high performance building envelope, we had our makeup air and IAQ component. Now we get to the next component, high efficiency combustion core. Now, I want to see at least 90% efficient combustion, which means we have to have a secondary burn that burns probably above about 2000 degrees Celsius to get complete secondary combustion that is in the secondary. So secondary combustion will be typically above 2000 degrees Celsius to get complete combustion of pyrolytic gases that are coming around the bin. I see Paul has a question.
Yeah, above 2000 degrees Fahrenheit, I think is difficult to achieve and possibly not desired. But you're saying Celsius. And so what does that work out to? Isn't that, if I'm doing the math right, isn't it double?
Not quite. No, I'll go back and look that one up. I was using some numbers out of this book.
Yeah.
I'll go back. Let me go back and double check that. I may have swapped them out.
I think we're pretty much going with a real clean burn.
Yep.
And hitting 0 on carbon monoxide.
Yep.
When we're hitting temperatures above 1600 Fahrenheit. And usually for a rocket mass heater, we're like, if we can be pushing 2000, not necessarily hitting 2000. Yeah, see, so here's Trevor saying 2000 C is about 3600 degrees Fahrenheit. And it's like, we're not coming anywhere near that. I kind of feel like the hottest rocket mass heater we have, Ernie felt like it's possible that under the right conditions, we might touch 3000 degrees, which we don't want to do.
Yeah, so I may have pulled, I'm looking at my notes, I may have pulled the wrong, as I was doing all the Fahrenheits and so forth, I may have pulled that wrong number, right?
I think if we're going over 1800, we are doing amazingly awesome. That is dreamy. And then we don't want to go somewhere around 2300 is where we start, where we don't want to go there. We don't want to get that hot.
So I'm not actually specifying that in the written spec. I'm just saying that we have to have over 90% efficient in combusting the fuel.
Okay.
So I'm trying not to be too prescriptive. I'm just basically saying we have to have the super high efficiency, right?
True efficiency as well, not the labeled efficiency that comes on modern wood stoves.
Right. Now I'm talking about actualized work. So part 5, immediate radiant heat emitter. So the system should have a means of providing immediate radiant heat to warm the space while the heater is burning. The percentage of heat radiated immediately versus stored in the thermal mass for release over the following 24 hours should be balanced to immediately warm the space to a comfortable temperature during the same period of time it takes to charge the thermal mass to keep the space warm until the next burn, right? So this is part of your engineering for any carbon negative mass heater, is to engineer that percentage balance between immediate radiant heat and thermal mass, okay? Part 6 is their thermal mass storage. Probably we want about 24 hours. We're going to try to go for a system ideally that gives us a daily burn, right? So we'd like to have enough thermal mass that when we store the excess heat coming out of the system in the thermal mass, that once we've charged it, it can maintain comfort heat for 24 hours, okay? Part 6, a passive exhaust system. The system should exhaust to the outside passively through a chimney system, not requiring a fan or other active components, okay? For a lot of reasons, including system robustness and everything else, passive exhaust is highly desirable in a carbon negative mass heater. And what we have here is a picture of what typically comes out the exhaust, which is almost completely water vapor and carbon dioxide. That should be almost 100% of what's coming out of that chimney, okay? And the 8th component is the long burn operational cycle. Since the dirtiest parts of the burn happen during startup and burn completion, the ideal is to maximize clean burn time versus startup and shutdown time. To do this, the operational cycle should ideally be designed for a single long burn each day, with the thermal mass carrying the system over to the next day's burn. We don't want to be start it up, close it down, stop it up, because every time we do that, we lose efficiency in the system. And those are the few moments in which we have less than optimal burn, and we can release a little bit of particulate matter, possibly a little bit of carbon monoxide into the system. And so we'd like to reduce that inefficient burn to the smallest percentage of time possible. And the best way to do that is to have a long burn operational cycle instead of a frequent stop start. Yes.
There's somebody is saying, asking a question in the chat. Clay is saying, why is a daily burn preferred over less frequent burns?
We would love to get to the point where the other parts of the system are efficient enough that in many cases you don't need to do a burn. So we would love for your passive solar, your high performance envelope, your thermal inertia, all of your other things are like, I don't need to burn today. When I say daily burn, what I'm saying is, let's just say that it's super cold out there, right? And that it's overcast, you're not getting passive solar, that sort of stuff. We don't want for you to have to burn 2 or 3 times a day. We don't want for the system to be like, oh, I burned once this morning and now I'm going to do another burn in the afternoon just to stay comfortable. So when I'm saying daily burn, when I'm going to write it all out in detail, what we're saying is ideally, even when it gets dang cold, we should not have to go off burning more than once a day. That's what I mean by long burn cycle. Okay, hope that makes sense. All right, so those were the system components. To be a carbon negative mass heater, according to my definition, it must have those components, right? So let's talk about the attributes now of this system. What are its behavioral attributes? The first is clean combustion and low emissions. That should be a Fahrenheit there to fix that, since secondary combustion temperature is usually around 2000 Fahrenheit, resulting in a very complete burn. As we said, about the only exhaust products released from the chimney are carbon dioxide and water vapor. PM 2.5 and PM 10 products, along with nitrogen oxide and other pollutants, are practically non-existent except for small amounts produced during system startup and shutdown. Okay. And what I have here, by the way, is a table showing the BTUs per cord for a lot of properly dried wood. You might want to look and see is poplar on. Try to see if poplar was on this one again, because we're going to use poplar coppice as our case study in a moment. Okay. How about high combustion efficiency? The combustion efficiency of well-tuned system can be around 95% in real-world situations, well above the realized efficiencies of other so-called high-efficiency wood-burning heaters. The result is much more of the fuel's theoretical heat capacity being released to become available to the rest of the system. This is how we're getting so much higher full system efficiency, is we're getting true high efficiency combustion, right? But we also have high heat retention and use. That is because we are storing the heat in a thermal mass before it goes up the chimney, the exhaust temperatures are much lower than in other wood burning heaters. In other words, this is another place where we have a huge advantage in system level efficiency. The exhaust from fireplaces and wood burning stoves is usually 600 to 800 degrees Fahrenheit, according to the system. Masonry stoves normally exhaust between 200 and 400 degrees Fahrenheit. And a good mass heater's exhaust is normally under 200 degrees Fahrenheit, often under 150 degrees Fahrenheit if the system is properly designed and properly optimized. So if you think about the difference between 600 to 800 degrees of exhaust going out the chimney, how much heat is coming out of the chimney and being lost to the outdoors. This is another place where a lot of wood burning systems lose system level efficiency. And that's why they're so much lower. It's why Paul keeps on telling you that you can heat a house with a tiny fraction of the wood. And of course, the exact fraction is dependent upon compared to what? A well-tuned masonry heater, or a catalytic wood burning stove, or a high, lesser efficiency wood burning stove. What that is, it can be a third as much to, in some cases, a tenth as much, according to what you're comparing it to. Yes, Paul.
So if I were to throw out some numbers for you, like let's say 100% is going to be a conventional wood stove from 30 years ago.
Yeah.
And then you could also select a modern wood stove and a masonry stove and then a rocket mass heater or a carbon negative mass heater.
Yeah.
I wish, because I get a lot of flack for suggesting my number, which is a rocket mass heater will heat your home with 1/10 of the wood.
Yeah.
What would be your numbers for these three scenarios that I've laid in front of you, first starting with a modern wood stove?
I don't have exact numbers I'll quote here because I don't have the science behind that right behind me. I have some anecdotal numbers-ish, but the one thing I would wish, me being the engineering type, my question always is like Paul says, it'll heat with 1/10 the wood. And my first thing is, please say of what? 1/10 of what? Because that I think is one of the places where there can be some 1/10 of what?
1/10 of the wood. 1/10 of the wood.
Of 1/10 of the wood used by what?
A conventional wood stove, which to me, a conventional wood stove is going to be a wood stove from like 15 to 30 years ago.
Okay.
Basically a metal box.
I'll agree with you because we're talking about, and I would say systems efficiency, right? A wood stove, conventional wood stove you buy 20, 30 years ago versus a rocket mass heater. Yeah, you're going to probably get in the order of magnitude of 1/10 of the wood, right? Yeah. If you're talking about like a modern, properly installed masonry heater with an exhaust that's tuned to 200 degrees, then you're not going to use 1/10 of the wood. You're going to use more than that, but you're still going to use less because that masonry heater is not going to have as high a combustion, and it's not going to have quite as high a retention. I think that's where you're going to get to that, closer to that number that you said of maybe 1/3 to 1/2 the wood, but maybe 1/3.
I usually state that a modern wood stove, usually there's a lot of different ways that they go about it, but they're usually going to heat with about half the wood.
Yeah.
And then a well-built masonry stove. And I gotta say well-built.
Yes.
Because there's lots of opportunity for comedy there.
Yes.
A well-built masonry stove is going to heat with 1/5 the wood. And then a rocket mass heater is going to heat a home with half the wood of the masonry stove.
Yeah.
Yeah.
I think you're probably in the right ballparks there. I think that laying it out in that way might help people understand what you're talking about a little bit better. Because as an engineer, I'm always saying it heats with 1/10 the wood. I'm like, compared to what? Give me your baseline of comparison, because otherwise I don't know. I'm not certain where we're going.
Right.
All right.
I've always gone with conventional wood stove.
Yeah.
And so I think to me that phrase means basically a metal box with a chimney on top of it.
Yeah. Okay. Another attribute of the system: low embodied energy. That is embodied energy, where we define that as the energy used to produce a product, including the energy needed to extract and mine, process and transport raw materials, manufacture and ship subassemblies, manufacture, pack, ship, and deliver the final product, right? So a large percentage of a typical mass heater is made up of the thermal mass, which is normally sourced out of local natural materials. The manufactured components, such as fire brick and steel, are long-lasting and comprise a small percentage of the mass of the unit. The passive design means there's no electronics, which means that there's not all of the embodied energy, embodied pollution, embodied carbon, all of those components. So when we start looking at what does it take to build the system, okay? And also, if I'm running an electrified system, and I'll get back to this a little bit later, if I'm running an electrified system, then I have this little dirty secret. It's called the electrical cable goes somewhere, right? The electrical cable is connected to a thing. It's called the electrical grid, and that has a huge, huge footprint. So if we're going to be honest about the embodied energy, not only do we have to talk about the embodied energy of the unit that shows up on the pallet and gets installed, we have to talk about all of a sudden, we're going to have an electrified unit amortizing the percentage of the entire power grid all the way back that thing is using. It's a tiny sliver of the entire power grid, but boy, that entire power grid is a massive footprint, right? So if we were being honest, we would have to account for that. And therefore, since this system is completely passive, doesn't plug into a wall anywhere, right? It has no electronics. It has a few very low tech components, some steel ducting, maybe a steel barrel, and maybe some fire brick and some other things, maybe some ceramic wool insulation, according to which method you are going to use to build it. Yes.
I'm trying to read the graph that you got there, and along the bottom, you've got 0, 50, 100, but what is it? Some of the font isn't coming through for me. What does it say?
Yeah, this is per embodied. I can't even read it here. This was something that came up from Dr. Lawson. So yes, fail on the font. I was more interested in showing the relative amounts. That long bar on the bottom, if you can't read it, is aluminum, right? The next bar is synthetic rubber. The next is copper. The next is plastic. The next is PVC. The next is acrylic paint. And then we finally get to galvanized steel. And then down from there, glass and on down, right? So this is just showing embodied energies of common materials that we use to build things with, right? And that's something that we use, we actually calculate when we're looking at, when we build buildings, what's the embodied energy, what's the embodied carbon. And I also like to calculate what's embodied pollution, okay?
So there's a number, there's a metric here, and what you're saying is that your carbon negative mass heater has to have a number on this scale that's less than.
Yeah, what we're looking for, what we're saying is an attribute of the system is it will have a very low embodied carbon compared to its competitors, right? It will also have low embodied pollution. It's defined as the amount of pollution created as a byproduct of manufacturing, packaging, shipping, and installing a product. So the amount of pollution created in putting together a mass heater is much smaller than that of any conventionally manufactured conventional HVAC system, and similar to that of a modern masonry heater, ballpark. Okay, how about low embodied carbon? Embodied carbon is the amount of carbon released into the atmosphere as a byproduct of a product's manufacture, packaging, transport, and installation. Embodied carbon is quite low, mostly coming from the fire brick and the steel used in construction. What you're seeing here is I'm interested in what's called life cycle carbon, not cradle to gate. Cradle to gate is extraction of raw materials and then manufacturing it. The gate is when it goes out the back gate of the manufacturing plant, right? Embodied carbon. No, we need to look at the life cycle, which is transporting it, installing it, using it, demolishing it, recycling it, everything else. That's the only true metric. So we use life cycle carbon, not cradle to gate carbon. Okay. How about the system dynamically sequesters carbon? As we're going to clearly see here in the case study, a properly operating mass heater can be massively carbon negative. And it is the trees that are growing our biomass for us that allows that to happen. And it has the cleanest whole system footprint. A carbon negative mass heater has a radically smaller whole systems footprint than any of the alternatives when you conduct a source to sink analysis. Any system that uses offsite generated energy must include the amortized pollution, carbon, and energy footprints of the energy production, distribution, and delivery systems, okay? And I would argue that it is biophilic. I do a lot of work in consulting on biophilic design, and the biophilic design is becoming a huge thing in green buildings. There's an understanding that buildings have an impact on the people that are in them. They can isolate them from the natural world, or they can actually reconnect them to the natural world. And so there's a lot of dimensions to this. It's a huge field of design. But I'm going to argue that an overlooked dimension of heating with wood is that the practice of operating a wood heater has the additional benefit of connecting us back to the cycles of nature and to the primal element of fire. Simply setting a thermostat and forgetting about it has the side effect of isolating us from the cycle and seasons of the earth when we're inside the building. So I think this is an important dimension to finding a way of heating with wood that is extremely clean. All right, let's go to carbon calculations for a sample case. With many thanks to Robin Stewart for helping me with this. Robin has her master's degree in chemical engineering. I forget how many patents, how many publications. She worked as one of the Environmental Protection Agency's lead carbon combustion specialists for, I think, close to 2 decades. So she is eminently qualified as a world-class expert to help me run these numbers.
Maybe we need to see Robin's credentials with her name, just like we saw yours at the beginning.
Yeah, I need to pull that all up. I have her CV, which is many pages long, and with all her publications and all her patents and all of her qualifications. We'll just say that I think she and her tenure at the EPA as with carbon combustion. We'll just say, I think it's safe to say that she is a world-class carbon combustion chemist. Okay, so I had her work with me to create this sample case. And here's the case study. We decided to see how good we could get. Fuelless dried poplar wood produced via coppicing on 1 hectare of land. We decided because we could get research for this, right? We also knew what the BTUs per cord should be properly dried poplar wood. We are running a harvest of 40% of biomass each year. The reason for that is that there is a paper that we were able to find in which the soil organic matter sequestration, poplar, coppice, was documented. And they documented that 40% biomass harvest provided a very high amount of soil organic matter per year, as it was a sweet spot. So we said, okay, let's harvest at 40% of biomass per year. The combustion core we're going to use is a reference 8-inch rocket mass heater, specifically the one that is documented by Ernie and Erica. Okay, so we have reference information for that. We are going to assume that 6.67 pounds of fuel is used on average. This is close to the amount that Ernie and Erica documented for their system, and that we are going to burn it 6 hours per day for 120 days per year. Now, that could be a burn in multiple buildings, right? That might heat multiple buildings, but we're going to say that we're going to have a total burn of 6 hours a day, and we're going to need to burn it 120 days per year. That's a dang lot of heat. Okay, so that's how much we're getting off. When we ran the numbers, that's the amount of wood we were getting off of a hectare of land with poplar wood production and a 40% biomass harvest. Okay, let's do the science. System carbon flow diagram. This is what we worked out for the system carbon flow diagram. You can see the atmosphere here. You can see that water, carbon dioxide, and oxygen is coming out. It's going to coppice and pollarded trees. The root exudates are driving microbial growth, which is going to sequester carbon and soil organic matter. You're also going to have composting leaves and twigs, which are also going to build soil organic matter. Woody biomass runs into a rocket mass heater, which of course produces heat. There's a small amount of ash and unburned carbon, which are minerals, and we can take that ash and unburned carbon and return it to the forest as well. And outcoming is water and carbon dioxide. The water vapor feeds back into the atmosphere, and the carbon dioxide can feed right back into the atmosphere. We also documented that you could do a rocket mass heater slipstream CO2 to take some of the central carbon dioxide and use a greenhouse as a CO2 scrubber, creating fast-growing biomass, bringing in oxygen, but also releasing oxygen into the atmosphere and further reducing CO2 as an optional off-gas treatment system. So this is an option. We did not include this in our calculations, okay? So that's a quick and dirty carbon flow diagram. And now what we're going to do is we're going to do the calculations. So here's our rocket mass heater inputs. You can see stoichiometric and complete stoichiometric combustion of bone dry wood and how that works, right? And now we're going to say, here's our 6.67 pounds per hour, 6 hours a day, okay, which works out to 40 pounds per day, 120 days is 4,800 pounds we're going to burn total. Yeah. So our woody biomass is 4,800 pounds. Moisture content is 20% because we write it down to 20%. So that's 960 pounds of water vapor that will, water we have to drive off, and bone dry biomass of 3,800 pounds approximately. The wood heating value of dry biomass for poplar is 8,337 BTUs per pound. We're going to use efficiency of combustion of 95%, and we're going to have mineral content of approximately 1%, so that we're going to produce about 38.4 pounds of mineral content ash side effect from all this burning. Okay, that's the calculations for the input side. How about the output side? All right, outputs. We're going to produce about 3,000 pounds of water in the form of vapor. Our carbon dioxide is going to be about 5,299 pounds, or about 5,300 pounds. But if we look at the percent of that that's carbon, we have now emitted about 1,446 pounds of carbon from the combustion. We've produced a little over 30 million BTUs, produced about 190 pounds of char and about 38 pounds of ash, right? Assumptions: ignoring nitrogen in the process unless there's a risk of creating nitrogen oxide compounds during combustion, and excess air required for complete combustion. This is not added to the values above. It just goes through the system, okay? Now let's do our biomass calculations. We are at about 8.6 megagrams per hectare per year. And we show basically how we produce that 4,667 pounds of poplar biomass dried down, because it produced 7,584 pounds of greenwood, dried down to 4,667, okay? And that's what we combusted. Now, from the paper that you see there by David Johnson, Dr. David Johnson, he was able to, with the coppicing system that we talked about, sequester 20,000 pounds per hectare per year without the use of grazers, and 40,000 pounds per hectare per year with using grazers in a silvopastoral system. So we're just going to assume we don't even do the silvopasture. We're going to just do the coppice. That's it. We're not going to even bother with this, right? Because if you did the grazers in the system, we can double the amount of carbon sequestration. So let's just even assume we don't even do that. We just do grazers. We have an exhaust of basically 1,446 pounds coming out of the rocket mass heater, but we have sequestered 20,000 pounds, both in the trees and in the soil organic matter. Okay, so let's summarize our case study. We have over 30 million BTUs produced in this case, 1,446 pounds of carbon dioxide released by the heater, 20,000 pounds of carbon dioxide sequestered by biomass production annually, a net of over 18,500 pounds of carbon dioxide is sequestered per year of operation of this system. Soil organic matter was building at around 0.5% annually in the system. That rate could probably be sustained until the soil organic matter started to reach saturation percentage, which could be well over 10% in many areas. This would allow for about 20 years of sequestration at the calculated rate before it slows down. During that period, a net of 370,000 pounds of CO2 would be sequestered. If this biological system was maintained as a fuel source, it would maintain at least carbon neutral, allowing indefinite system operation while remaining massively carbon negative. So there you go. That is the hard science of the carbon combustion chemistry of how this is massively carbon negative. You go to a system with grazers, we can make it almost twice that good. Okay. We ran through all of this, and I asked Robin, I said, is there any case you can imagine in which we could create an electric version of a heater that had this little pollution, this little embodied energy, and was also carbon negative when we accounted for everything? Her response was to laugh. She just laughed. And she said, if you need an official answer, the answer is no. I can't imagine any way of doing that. Okay, there's our case study.
Okay, I want to jump in real quick and say, for that particular rocket mass heater, I know which rocket mass heater is, and it's in a largish uninsulated structure.
Yeah.
And so basically, I kind of feel like if that structure were to be insulated and a few other things, it probably would need a quarter of that wood.
Exactly.
And so what you have outlined in my mind, as I'm hearing you describe it, I'm like, wow, that's a lot. But you left out the part of like, how big is the structure? Where is the structure located?
Right.
All that stuff. And it's like, I understand why you did that.
Exactly.
And yeah, it's like, doesn't matter. Those are variables we're not going to touch.
Exactly.
With this. Yeah.
Exactly. So what we basically said is we have a reference 8-inch carbon mass heater with measured fuel consumption rate at full burn. And we'll operate it at that full burn. We know now how many BTUs it's going to give off. Okay. Now we can take it to any building and say, we designed the building, here's how many BTUs, so on and so forth. We can run it at less than full load. We can do whatever. But we're just showing that if you ran an 8-inch reference, 8-inch carbon mass, rocket mass heater, 6 hours a day for 120 days, you would burn up what we coppiced off of a hectare. Okay. And in so doing, if you operate the system in that way, you would actually sequester 18,000 pounds of carbon net that you originally pulled all of this out of the atmosphere, right? And net, once you release some of it back from the combustion, you would sequester that much. Okay. Therefore, just the rocket mass heater as a combustion unit, which is where the carbon combustion comes in, with no scrubbing on the output, is that massively carbon negative. Okay.
So for a carbon negative mass heater,
yeah,
it has to have something resembling a rocket mass heater.
Has to have a high efficiency combustion core.
And it has to have something about the fuel source.
Yep.
Does it? Because part of when you and I first talked about this years ago, it seems like a major component of it was, what if we were, because I know that there's this whole concept of fuels reduction.
Yes.
And it's like, the idea is like, what if we use the wood that's being used as fuels reduction, and what they currently do is they go into an area that it's at risk for wildfire.
Right.
And they cut out a whole bunch of wood.
Yep.
And they put it in a pile and throw a tarp over it. And when January rolls around, there's lots of snow on the ground. They whip off the tarp and they set this pile of wood on fire, thus making the region smoky, like there's wildfires going on.
Yep.
And so you and I were talking about, like, wouldn't it be nice to use that to heat our homes instead of filling the atmosphere with smoke?
Absolutely.
In January.
Absolutely. And that, I think, if you look at that could also be carbon negative. It wouldn't be as massively carbon negative as what I just showed, right? But if we did it properly, then what you could basically say is still use the most efficient burn possible, still use the most efficient building envelopes possible, because now all we do is the same amount of fire reduction, of fuel reduction, heats more homes, right?
So I mean,
heat
part
more
of
homes that way, with the same amount of wood we got out of the fuel reduction program.
Part of the criteria that you listed was something about sustainably harvested wood.
Regeneratively harvested wood.
Regeneratively. Okay, good. Because I kind of feel like a lot of this fuels reduction stuff, they are doing that. The only time that they don't do that is when a wildfire is imminent, and then they do what they call a soft burn, which is polluting. But but as far as harvesting the wood at a time when there's no risk of wildfire,
Yep.
and it's to, reduce the risk, it does seem like generally they're using regenerative forestry practices. And I've recorded a podcast where we advocate for woodland care over regenerative forestry practices. And that's another story for another day.
Yeah.
But the key is that it's like, because the thing I advocate for is, like, for example, this building that I'm in right now, we measured it to use 0.60 cords of wood, which would be about a quarter of the wood that you're recommending, maybe even less.
Mm-hmm.
So whereas you're advocating a coppicing system, I'm thinking this amount of wood is so small that it could be, and I'm going to say a thing that you kind of referred to earlier. It could be nothing more than the branches and twigs that you pick up out of your yard every year.
Yep.
It could be because it's such a small amount.
Right.
In which case you're not, because if you've got 2.5 acres, a hectare of wood, that's a big piece of property. I mean, when you get onto an acre, and in fact, I kind of wonder about saying a hectare, like if you're in a coppice, 40% of poplar trees, and it's off of an acre of poplar trees. I'm kind of thinking like, ooh, that's a lot of work at all. And I would imagine that the amount of wood that you would get from coppicing 40% of the biomass that's above ground would be such a huge amount that an acre might equal the amounts that you're talking about.
So the reason we ended up using what we did, the hectare, was you see down there at the bottom, I have something very important called references.
Yeah.
This is because I can pull the numbers that we are using this table out of peer-reviewed published papers. So we came up with a case study that we could hopefully at some point publish, in which all of the feed information can be referenced back to published information, so that people say, well, where did you get that number? Where did you get that number? We can say, here it is, right? So it's like, this is an example case study, which is basically designed to do two things. One is to be rigorous in the science so that we can publish it and people can't argue with it. And number two is I wanted to show that we can be not just a tiny bit carbon negative, but massively carbon negative.
Yeah.
Because what I'm going to do is I want to go into the people who are telling me that I have to electrify in all cases and put this down as a challenge and say, if you can show me how to do better than that with electrification, I will.
Right. So then I like the part where you said this could be multiple homes.
Oh, yes.
Yeah.
Yeah. So that's what we're saying. I'm just looking at the combustion, like, I'm looking at the system and saying this could be many rocket mass heaters across many homes, right?
Yeah.
To give us a total of 6 burn hours a day for a total of 120 heating days where we need to actually heat. Okay.
Just so people know, my rough math says that what we're talking about here is 2 cords of wood, roughly, give or take a half a cord.
It's probably that neighborhood.
Yeah.
Okay. So let's go to a comparison to alternatives, so we can kind of finish up here. So we have to talk about something called EUI, energy use intensity. This is something that when I'm doing LEED buildings and other kinds of things like that, I have to calculate EUI for the building, and it stands for energy use intensity. It's calculated in several different units, but the most common in the United States is BTUs per square foot per year. In other words, how energy intensive is this building? And of course, what you really want to know is, in order to be able to compare one building to the next, is how much energy does it use per square foot every year? And so what we do is we take and we convert all the energy you use to BTUs, which is 1,000 BTUs, using these conversions. Here's how you convert a kilowatt of electricity. Here's how you convert a cubic foot of natural gas. Here's how you convert a gallon of propane. And so there's these conversion rates, right? So you then compute that by you add up all of you add up all the different energy uses, right? And then you divide it by the gross square footage of the building, and that will give you an EUI. And we'll just say that a 156 is not really that's pretty dang bad. We'll just say that, okay? But that would be a realistic number though. However, I want to throw in something else that you have to talk about. It's source versus site EUI. Because when you do that number, if you just calculate based upon, let's say, how many kilowatt hours did we use at the meter, you're doing site energy use intensity, not source. You're not accounting for all the losses in transmission, right? The source actually takes and says, here is my source. If it was coal, right? If we want to do apples to apples comparison, then I've got to go back and look at, here's the coal that you burned. Okay, what percentage of that actually got turned into electricity in the first place? What percentage of that made it to the site based upon transmission and distribution losses, right? Okay, that gives us a number when we take all of that into account called source EUI. To me, if you're going to do a real analysis, you have to do source EUI. Although most numbers quoted are site EUI, it hides all the losses in the big infrastructure, distribution, transmission, etc. Here is a table that I pulled together, source versus site EUIs for different kinds of buildings that are common. You're going to see that a fast food restaurant is about the worst thing you could find. And it makes sense. If you think about everything that's going on in a fast food restaurant, 886 kilo BTUs per square foot per year. Yikes. Okay. Now, EUI is oftentimes calculated for just commercial buildings. It's not often used in single family dwellings. It's sometimes used in multi-tenant units. Okay, so oftentimes you won't see this. I've done some EUIs and I've seen source EUIs for a lot of homes in the 50 plus range. Okay, so the reason I'm pointing all this out is to say that when we start to really do apples to apples comparisons, if we're going to look at how effective and efficient a rocket mass heater is or a carbon negative mass heater is, we really have to insist that we do source EUI instead of site EUI. Okay, so I'm not going to have time to go into all that math. We're just running it. So, and there's still a lot more analysis for us to do. But I can tell you that by using all of the strategies I've talked about, passive solar, annualized thermal inertia, geothermal tubes, green roofs, high efficiency building envelopes, I'm looking at a building that I'm building for an eco-village project right now in central Alabama. Our guesstimate is those buildings will need a 6-inch rocket mass heater, 400 square foot per side of a tiny home duplex. My guess, based upon my best calculations at the moment, is that our EUI, including the rocket mass heater, will be, source EUI will be about 3, okay? Maybe 4, okay? Yeah. All right, so that gives you an order of magnitude that we're looking at. So when we come down to a final comparison, I think we can show with hard numbers, much more efficient than any other wood-fired alternative, much lower technology in embodied energy, pollution, carbon footprint than even a geothermal option. Electric heat pumps require electrical infrastructure with the energy pollution and embodied carbon that brings, which means that amortized stuff is in there, plus all of the high tech and footprint of building all of the heat pump stuff, maintaining it. Solar PV powered electric options have the problem that power generation is often lowest when heat is most needed. I have now a couple buildings where I've done this. I have buildings that are fully off grid. That is, they have no grid connection. None. What you start seeing is, and this is an important point, when I go in and I start talking to the folks that are running Living Building Challenge certified buildings, they are, in almost everyone, they are grid connected. And what the Living Building Challenge requires is that the building produce 105% of its energy footprint annually. In other words, you have to actually produce more than you use. However, let's pull up the little asterisk and look at the fine print. What they're doing is they're producing surplus in the summertime when the sun is beating down on their head, and they're feeding it back into the grid. Then in the wintertime, when they can't produce enough power, they're pulling from the grid, which means if you really want to do the analysis, you have to include the grid. When I am completely grid independent, I can't cheat that way. The Allahogi project that we're doing for the Muskogee Eco Village in central Alabama has to be completely off grid, which means I cannot cheat that way. So if I were going to try to make this electrified, I would have to massively oversize the solar panels and massively oversize the batteries. With all of that embodied carbon, all that embodied pollution, all that cost, all of that embodied, energy, all of it, it's massive. And so I've said to them, look, I have to use wood combustion because it is massively more efficient, massively cleaner, right? And it allows for us to properly size the solar and use the solar for what it's good for, right? Now, what's interesting, and I've already done this on a building that we've built, we were able to drastically reduce the size of the solar array to run a community building of 3,000 square feet. Because when we did the analysis, it said, no. We're not having to heat the building. That's happening with rocket mass heaters. That building has two 8-inch rocket mass heaters in it. And by the way, both of them are fully ASTM masonry heater qualified. They meet full standards. So they could be insured and they're code compliant because they're full ASTM. We had Erica fly down and supervise the builds. They're beautiful. And therefore, in the wintertime, we are using carbon negative mass heater to heat the building, which means we don't have to try to do it. We have a geothermal heat pump, and that's what's cooling the building in the summertime. For those of you who are familiar with the SEER ratings, that particular variable refrigerant flow geothermal heat pump has a SEER rating of 42. Therefore, we're able to use a smaller solar array. And interestingly enough, when is the highest power demand coming from the heat pump? Typically in the moments when the sun is beating down on the solar panels. So by carefully considering all of this, we were able to drastically reduce the size of the system and the size of the batteries. And so now it's, well, we just run, when we got all kinds of power coming from the sun beating down on the solar panels, we cool the building. Because yeah, it can get 103 and 105 degrees out there, right? We keep the building comfortable because this is the heat refuge for the elders in the village, right? So this is our, if we have to, this building can be guaranteed to be kept at like 72 degrees, 75 degrees as a heat refuge for people who need it in the village. But this shows that we can take and properly engineer a carbon negative mass heater into a larger system so that it benefits the solar panels and works symbiotically with them, allowing us to downsize and decrease the footprint of the solar panels when they are built properly. Okay? Yes.
On the previous slide, you mentioned something about energy losses through the wire. I'd like to get an idea because it seems like about 15 years ago, I saw some analysis that was saying that energy losses could be as high as 90%.
Those numbers are high.
And then more recently, I can no longer find anything about that. Everything I'm finding is closer to 9%.
So that number is closer on transmission, okay? You have two different numbers. As electrical engineers, we have to do two different numbers. There is transmission and then there's distribution. Okay, so my understanding, and I don't have these numbers on the slides. I need to go pull them. This is where I need to finish up this presentation with those numbers. I think you're right that it's around 9 or 10% on transmission, but there's some additional loss in distribution. What that means is, for those of you who've seen it, those big, huge transmission lines that run from where the power is generated at the, like the natural gas plant or the coal fire plant or the nuclear plant or the hydro plant or whatever, where you transmit it over long distances at very high voltages, that is transmission. Now you get down into a neighborhood, you go to a substation, you step it down to an intermediate voltage and you distribute it in the neighborhood, and then you distribute it down to the house. That's distribution loss, okay? That's another percentage. And so if we add the whole thing up, we have our total, that's what we are working with how much loss we have from source to site. And site starts when we hit the meter at the building, right? How much energy do we use there? That's the number where we do a site EUI from. The source requires us to go back and see how much power did we crank in at the source in order to get that result out at the site. And that is why I'm insisting we use source EUI. It's the only valid number to use if we're going to do a system level analysis.
Okay, so I'm curious about what kind of number are you seeing for the total, like what's total loss?
Ooh, I'm trying to remember. I had that number. I'm trying to remember what the exact number is. I think today we've gotten it down to around 20%.
Okay.
But don't quote me on that yet. I hate to quote numbers that I don't have exact.
Fair enough.
So, yeah. And of course, that is just loss in transmission and distribution. It doesn't include loss, for example, if we burn coal, and how much of that coal goes through the steam to be turned into electricity in the first place. So that's actually another loss that has to be calculated in there, right?
Right.
That can be quite large.
I mean, you're right. There is a lot of losses that happens, in energy. It's like a lot of those are only 30% efficient.
Yeah.
But I kind of feel like, yeah, that's kind of part of that particular medium. And you could choose to count that, or mostly what I'm trying to wrap my head around, because I found the numbers to be really squirrely.
Yeah.
And when trying to make the point. And so I've been seeing transmission is 9, and this is the first time that I've ever thought when they're saying transmission, they're saying like, oh, step 1 is 9.
Yeah.
Step 2, 3, and 4. Well, that adds another 11%. And it's like, now things are starting to make more sense.
My next step is, I am an electrical engineer, but my next step is to go find the right power systems engineer. Mm-hmm. It's a specialty in electrical engineering, right? And actually go through the source to site analysis and run numbers and show what the actual numbers are and how much carbon we're producing per kilo BTU when we take from electrification and are burning natural gas or coal, having all those losses into steam fire electricity through all the distribution and transmission losses, and then through the heat pump and so forth to get the same amount of heating that we're getting from burning a certain amount of wood, right? And compare those numbers. That's the next part of this analysis, right?
An interesting thing to do, just natural gas, like a natural gas energy power plant generating electricity, which then comes through the line.
Yeah.
And then like, okay, so what's that footprint look like versus having natural gas piped to a house? Now,
just saw a note here from Paul T. Says he's not mistaken, percentage efficiency of distribution transformers will decrease dramatically if the load is low, and will increase as the load increases closer to the rated capacity. That is correct. Yes. So the load on the grid doesn't change much regardless of the end user load. That's a little harder to say exactly. It does, but the efficiency does go down. Yeah. So, but we need to characterize that. That's why the distribution, boy, this gets, like you said, it gets complex. That's why we need to kind of like come up with like average case numbers, characterize the whole thing, and get it down to, again, referenced numbers that go back to something that I can call out, so that when people, want to argue with me, that we can go back to, something that is defensible, right? It's not hand wavy.
Speaking of people that are going to try to argue with you,
right?
I wonder if you're going to come up, like in one of your slides in a moment, about the solution of mini split with solar power.
Yeah. And so that's one of the things I've done before, is mini split with solar power. When you get to a certain size of building, then geothermal with solar power becomes more efficient, right? It's just that when you start looking at small buildings, like going to all the stuff of doing geothermal and drilling all that kind of stuff, it's just not as efficient, right? Because you have all the stuff you got to do that. When you get to a large enough building, there's a cut over to where geothermal seems to be a better bet. So I've done a larger building with geothermal and know how that works. That building is operating right now, and so I can say definitively how that works. We are just finishing the build of the tiny home duplexes. Those are the ones that we think are going to have such a blastedly low EUI, and we're going to metric those and document them. And I'm also going to put some indoor IAQ, indoor air quality meters in that to document the indoor air quality.
Okay.
So those are things that we're getting to.
When trying to look up the efficiency of a mini split, there's a lot of information that's conflicting.
Yes.
And so some rather official organizations seem to say that a mini split is going to offer a 30% efficiency. It's going to be 30% more efficient. So basically you're going to heat your home with 30% less electricity than if you heated your home with electricity in a more conventional fashion.
I've heard numbers like that. I have not seen definitive science on it. So I do not know yet how much of that is industry hand waving and how much that's true. I do know that they do seem to pull less, but we have not yet put numbers on it, hard numbers on it that I can defend yet.
Okay.
There's a lot of science here. I mean, we need folks in our community that have this background to help us do this, right? And to actually put it in here and get this published. Somebody asked, do I have an air meter you recommend? That's a complicated question. Because you can get all kinds of different air meters for different uses, and some of them tie into telemetry. I know Paul has one. I know Gary, I need to go back and find out the one Gary has landed on, because I've been using ones that are basically connected. That is, they connect back to a back-end data logging server, right? There's other, and I use like SenseWare and other people like that for that. But then there are ones that are just a little standalone. And I need to go back and remember which one Gary has, because he's kind of done some research and come down to that one. So yeah, if you'll ask on the Hermes forum, I'll ask Gary and see if we can get the one he came down to. Yeah, that would be, that's how I'll answer that question for right now.
Are we coming up on the finish line of this presentation, sir?
Yes. So
I called it.
Yes. Yeah. I haven't played with the Davis. If you have any good recommendations or anything, just message me on that. I would love to hear about it. So yeah, I think from here we can maybe take a couple questions. And I know there's an infinite number of questions we could go from here, but maybe we can take a couple quickly and then wrap up. And if you don't get your question answered, then maybe we can have a few questions and answers on the Hermes forums after this.
Yeah.
So I'll let Bo kind of tell me if he's got how he wants to do it. You want to have people unmute and ask a question, or in the chat, or what do you want to do?
So I'll ping the folks who had questions that we saved for now. Paul, folks are still on the call. I've just asked you to unmute and ask your normal planetary climate shift question.
Okay.
Yeah, Alan, that was excellent. My question was, we can undo what basically we've done, but how do we manage the normal, I guess, the planetary shift in climate, which is an area that isn't going to generate money, so isn't on anyone's political agenda.
Right. So what you're seeing now is more and more, as these numbers have been run in the building community, Like when you do the lead AP test, one of the questions you're almost certainly going to get asked is what percentage of carbon emissions are buildings responsible for? And the answer is almost 40%. So that's just sort of an interesting thing. But when you start getting into these discussions, what you're starting to see now is people are finally starting to discuss what they have termed nature-based solutions, which is the recognition that dynamic sequestration, the way I talked about here, is really what we're going to have to do to resettle carbon and get back to something that is more stable. And when I go through it in detail in the PDC, what we look at is we talk about the Earth as an Earth space battery. That what's happening is the more carbon we have in dynamic sequestration, the more the battery is charged. That is, we have what's charging the battery is incoming sunlight. And if we could take and start to move the amount of biomass back towards what it was pre-industrialization, we can actually pull the CO2 back down to pre-industrial levels. That includes restoring rangelands, protecting peatlands, restoring silvipastoral systems where they were, restoring forests, restoring canopy and land use patterning in cities. All of these things are things that I've been working with in land use patterning. So to me, the cutting edge stuff that we're looking at right now are developers who are wanting to talk about the land use patterning that will allow us to reach this. And what we're able to show is that the developments that you can do on this produce a higher quality of life and are less expensive to build and less expensive to operate. So there's your financials on it. Boy, it's a long conversation, but I think we're now getting to the point where we can actually show, and we have developers that are getting interested in that. And the discussion on nature-based solutions are really starting to move. Yeah.
Cool. A number of people want to know if you can make your slides available or the content therein.
We can talk about that. I really want to go back and finish adding the stuff we talked about, and I think maybe we can discuss that. Yeah.
We'll get back to you all on that. Paul T, if you would find your mute button, you've got a cardboard related question.
Hi there. Yeah, it's just following up on Paul's point about using packaging cardboard as fuel for a rocket mass heater, whether that makes it carbon negative. That was all really. And does it actually stop it, make it being carbon negative, because the cardboard obviously isn't carbon negative,
Right.
But does it actually stop it becoming any more carbon positive if you stick it in the rocket mass heater?
It's a complicated question because there are some people who would not have Paul's aversion to composting the cardboard, in which case some percentage of that carbon could go into dynamic sequestration according to how you did it. It'd be a small percentage or a moderate percentage according to how you did it. Paul doesn't like that because of the toxic GIC in most cardboard. And other people are kind of like, they believe that the toxic GIC gets bound up in the carbon matrix. So again, complex. Now, the problem we have is that a lot of the wood production that is driving cardboard today is very degenerative. And so I think what Paul's point was is like, okay, we've already got a problem. It's arrived on our doorstep, and what can we do with it? And that's one way of taking care of it cleanly while having the secondary combustion hot enough that it pretty much burns off a lot of the toxic GIC. And we neutralize the problem. I don't think if we did the full, I mean, you have all the transport, embodied energy, the transport of the cardboard, the manufacture of the cardboard, all the stuff in like industrial forestry practices and so forth. It won't be carbon negative. I just think of that as possibly a way of taking and using that resource that's already a resource that we shouldn't have produced in the first place, right? Let's solve the problem systemically. I mean, yeah, if you've got it and you have nothing better to do with it, it's probably the best thing you can do with it, but I would not think of that as a carbon negative solution, because it's like we have people going, oh, look, we solved the problem and it's carbon negative. No, you didn't. You're trying to mitigate a problem that you created. So that's how I would look at burning cardboard.
All right, Jim, you're up next with a couple questions.
Hi there, can you hear me?
I can, yes.
Wow, this laptop is actually working.
Yeah, yay.
I'm wanting to build a rocket mass heater to heat the greenhouse, which is now heated by electricity.
Yes.
I'll be looking for something that I can store as maximum amount of heat in, so I could have ducts in it to blow air through it when I need to heat the thing. I want to just keep the frost out. I don't actually want to make it warm. I just want to keep the frost out at night.
Yep.
I was thinking perhaps I could use pit run, which is just straight out the ground for the material. I don't know whether that would work or not. It's very
What
dense.
climate zone are you in?
Sorry?
What climate zone are you in?
About 7B-ish.
Oh, heavens. Yeah, you can do that without a rocket mass heater even. You could do that with a thermal battery. But you could use a rocket mass heater as well. I think, Paul, am I correct that Uncle Mud has a plan for, is it Uncle Mud that had the plan for the,
I think Erica has a plan, but Uncle Mud is going to be doing a webinar soon about heating a greenhouse with a rocket mass heater. There's also the thing that we have here, which is called the season extender, which is basically designed for greenhouses.
Yeah.
It's outside, so it gets wet.
Yeah.
I do, when it comes to greenhouses and rocket mass heaters, there was one thing that you mentioned in an earlier slide that made me cringe.
Mhm.
And that is that I kind of feel like whenever because you were saying take some of those exhaust gases and route them into a greenhouse. And I want to discourage ever saying that, not because what you're proposing is of course brilliant. You are Alan Booker. However, stupid people exist.
Yep.
And they choose to not read the fine print. And then Darwin has a theory about how this story ends.
I like that. We take them out of the gene pool.
So you're
Just
saying
kidding. I'm just
extra
kidding.
benefit?
Extra benefit. But no, I mean, it is, I mean, think about it. I've worked on systems where we go into commercial greenhouses and they are spending energy in order to concentrate carbon dioxide and increase it in the greenhouse to increase production. So it's like, all right, it's an option. It has to be a properly engineered option. It has to be engineered safely. So, you know.
Sure, you can say that all you want. And I think
Yep.
for every person who does it safely, there'll be 100 that don't.
Yep.
And so that's why I think that the whole idea is a horrible idea and no one should do it. And we should always discourage people from even talking about it because of the fools that will that will kill themselves doing it poorly because they didn't read the fine print.
Yeah. Well, I mean, this is talking out on a commercial scale, like when we're doing commercial greenhouses and so forth. I wouldn't typically recommend it for a backyard greenhouse.
I just want to emphasize the amount of carbon dioxide you raise is
Yes.
extremely small, extremely tiny.
Yeah.
And on top of that, the next thing is you could only do it like in the day, specifically probably only in the morning.
Yeah.
Because those plants need oxygen at night. And then on top of that, the fools tend to run the rocket mass heater without venting the exhaust outside inside the greenhouse.
Yeah.
I'm sorry. So let's just say I've developed a bit of a psychosis on this issue because of conversations with fools in the past.
Well, I could engineer a proper solution to it. So I think it's on the possibilities list. But no, it's not an amateur maneuver. It needs to be professionally engineered if you're going to do it.
Okay.
Yeah, I can take like one or two more questions. I know we could go on all night, but I do have to get to dinner here in just a moment. So what do we have that's
I have to run away. I hope you just have one more.
Let's
I was going to say, I would recommend Uncle Mud's greenhouse, rocket mass heater for greenhouse webinar then for the gentleman who was looking to do that. I think Uncle Mud will give you a lot of great pointers on that.
Let's do one Trevor, who was asking about the cooling effects of rocket mass heaters. Can you guys speak to that for just a moment? And then we can hit the rest of them in the forums after the fact.
Sure. What I would say is cooling effects of rocket mass heaters. Paul has the ability to do that because he is in a climate zone in which there is actually a very considerable diurnal swing in the summertime. What that means is it gets nice and cool at night. and then it gets hot in the daytime. And so he can actually use the mass of the rocket mass heater as a cool mass by chilling it at night and then allowing it to absorb heat from the house during the day. And that is a possibility in climate zones where in the summertime you have diurnal swings. In like the area where we're using them in Alabama, we don't have that kind of diurnal swing. You can get summer where it's 100 degrees in the day, and then it only gets down to like 78 at night, right? So what you're doing in those moments is you're just basically trying to keep the mass as cool as possible, right, as a thermal flywheel, but you don't have the ability to pull cool air through it at night the same way. So what I would say is, if you have a climate where in the summertime you do have nice cool evenings, then that is a possibility. Otherwise, you just gotta basically try to keep it from absorbing heat and use it as a cool sink as best you can. All right. With that, I think we'll have to go ahead and wrap up. We'll move other questions. I know there's plenty other things to discuss, but you can message me on Permies if you have any direct questions, or I think even better, Bo, we probably have a thread somewhere on Permies for this webinar. So you can also go there and we can throw questions there, and I'll try to answer those if I see them there.
Sounds great. I'll post the rest of the questions to the thread for this webinar, and Alan, I'll send you an email for those. But
Okay.
That's Alan, a little silent reaction of clappy hands. This was awesome. Thanks so much, Alan.
Very good. Well, it's been good to kind of roll through this with the audience, and it's kind of, a lot of this is sort of me getting ready to go do this for industry players, and in order to try to get them to recognize that this is options we've got to talk about if we're serious. Yeah,
that's awesome. All right, thanks everyone. Have a wonderful evening or morning if you're on the other hemisphere, Paul. All right, good night, everybody.
Good night, everyone.